Hello. How's everyone doing? No one's going to respond, right?
I'm doing good. Can you hear me?
I can hear you. Yeah, perfect. I always do that. It's like I treat it as a meeting, and it's like, well, it's a one-way meeting. It's not really, like we have people joining. So say hi in the comments if you're here. Welcome to Hoot number 63. This is the last Hoot of the year. And I'll be talking to Christian. We'll be talking about mutual authentication in Cilium. So Christian will take us explain what mutual authentication is, take us through that, and then explain how it suffers from eventual consistency. Right, this approach suffers from eventual consistency, which can produce some security vulnerabilities. It's definitely going to be an interesting talk. So as I said, if you have questions, say hi in the comments. Feel free to ask questions, and then we'll cover them as we go through, as Christian goes through the demo and the talk. How was that for an intro? Good?
That's good.
That's
I
good.
think that's good.
All right. Well, I'll hand it off to you. I'll switch the screen so everyone can see what you're sharing, and then feel free to go ahead and teach us what Cilium mutual authentication is.
Excellent. Excellent. So I just want to point out that, Cilium is a very popular container networking project in the CNCF. Kind of started off as a CNI and is a very powerful CNI. Here at Solo, try to keep this not very solo heavy, but just as context, here at Solo, we are big fans of Cilium, that we do provide production support with SLAs around Cilium CNI. And we think that is a good foundation for layering in security to your container environments, to your zero trust environments. But it's not the only piece. And we think that the service mesh plays a big role in getting to that next level of zero trust, being able to authenticate workloads and requests that flow between those workloads. And we see this application networking security as being implemented in multiple layers to get defense in depth. So I just want to say that as context, because as we look at some of the details here about how Cilium implements that next layer, right? So start off as Cilium as a CNI, but then that next layer, how do you get to the mesh capabilities? The Isovalent team has been working on an approach that kind of diverges from what every other service mesh does, and I encourage you to go take a look at some of the material that they've written about that. But we're going to look at what are some of the implications of an approach that's layered on top of Cilium, like what they're proposing in Cilium Service Mesh, and we'll juxtapose it to what does it look like in other service meshes. Specifically, if you're going to be comparing to sidecarless service meshes, ambient in Istio is obviously something we've been working quite a bit on here at Solo, that adds that service mesh layer on top of any CNI, but Cilium included, and solves some of those security challenges around zero trust. So if you go take a look at the new stack, and I think we'll scroll the link as well, a bit.ly link for the blog post. What I was trying to take a look at here was the the underlying Cilium identity model and how it identifies workloads in a Kubernetes cluster. And I'll actually start at the very end of the article to point out what Cilium does here. And actually, I'll go to a diagram that doesn't include some of these. The article, you can go take a look at the article yourself, but The diagrams I am interested in are right here. All right. So in Cilium,
Can you just zoom in a little bit more? Yeah,
yeah,
perfect.
yeah. So in Cilium, and I didn't go into the detail of. I should have probably put the pod IPs associated with each pod, but in general, what Cilium does is it creates this integer that identifies a group of pods, and those are based on labels, right? The pods have labels and so on. But in the cover, since the Cilium data plane is written in eBPF, what it does is it tries to map up the IPs associated with a group of pods and this integer, this special integer that Cilium uses for its notion of workload ID. So if your IP address of a particular pod lives in a group that's associated with this Cilium integer, Cilium ID identity, then we can write network policies, Kubernetes network policies that then enforce layer 3, layer 4 traffic, and allow, deny, whatever between namespaces and pods based on this Cilium identity or this integer, again mapped down to pods. And that's how a lot of the CNIs work, right? And what the service mesh efforts or the mutual authentication efforts were or have been implemented in Cilium today is how do we provide a way to prove and show that an application or a workload A, for example, is a workload A and that it is talking to a workload B, and that really is workload B, and that they trust that they know the workload identities between them. You may have heard of other projects tackling this problem, the workload identity problem, and the authentication problem. This is a very common, probably one of the top use cases for wanting to use a service mesh. And actually, I'll take a step back because some people walk in and they say, "Well, actually, I just want encryption. I just want encryption between my applications." You don't really need a service mesh for that, although they can provide that. As you'll see in most CNIs, Cilium included, you can get encryption on the wire between nodes, for example, in Kubernetes, using something like IPsec or using something like WireGuard. So although a service mesh has encryption, that's not really you can get encryption in other ways. But what typically you look at service meshes for is how can I prove that workload A is talking to workload B? That's where mutual authentication comes into the picture. Now, in a service mesh, let's say we'll pick Istio for example, but it doesn't have to be. It could be any service mesh that's implemented with a sidecar. It kind of looks like this, and I can zoom in more, right? The workload on one side, workload A in this case on the left-hand side, wants to talk to C. When it talks and opens up the transport and the connection to workload C, the little sidecar that's deployed with the app will transparently basically upgrade that connection so that it's using MTLS. And in that case, using TLS, the TLS spec offers a way to do authentication. Doing it in both directions, mutual TLS, allows us to authenticate each side using certificates, and those certificates can be backed by a spec called SPIFFE. SPIFFE is a specification for assigning workload identity, which is what we want in this case, is to know that service A is talking to service B, that they trust that is those are those identities, and those identities can be rooted in some other third party that attests that yes, indeed, that is workload A, or yes, indeed, that is workload B or C or whatever. And so in the sidecar takes care of mapping basically the workload to the workload ID or the certificate, and then from there, as the connection proceeds, you can trust everything else on that transport that it is workload A or workload C. Now, the way that Cilium implements its service mesh, we don't have this sidecar. And what ends up happening in the Cilium case is, if we let's back up a little bit.
And then
Right.
this in the service mesh, when you have workload to workload, right? That's the identity is tied to that workload specifically, right? It's
Yes.
workload's identity, and if it's going to be a different workload, it's going to be a different identity and a different certificate, right?
Yes, the certificates will be different. So if you look at the pod here, app A has a certificate that was issued to it and has been verified that this is app A. And so it will have the app A certificate. App B down here in this pod will have a certificate that says it's app B. And on this side, we'll see that this will have a certificate that says it is app C. And so when that connection is open and established and the MTLS handshake occurs, they will exchange those certificates. They will trust that those are the services that they say that they are.
And it's encrypted with the keys that are like negotiated between those two specific like workloads,
Yeah.
right?
That's the other thing that's guaranteed by the TLS spec, is that when these two applications authenticate each other, then they exchange session keys. Well, they don't exchange, they negotiate session keys that then get used to encrypt the communication and are only known to those two parties, right? Yeah. Oh, good thing to point out. In the Cilium case, when pod A wants to talk to pod B and they need to authenticate that those are indeed service A and service B, what ends up happening is the connection will first try to open to pod B. And what Cilium will notice once it gets into the networking layer or into the eBPF data plane layer is that this connection to pod B has not been authenticated. There's a new connection, has not been authenticated. We need to go through the mutual authentication process. And so what it ends up doing is it starts to drop those packets. And actually, I don't think in my demo, maybe we can try to pull it up on the fly, but you can look in Hubble and you can look at the flows, the TCP flows, and show that these packets are getting dropped because they're not authenticated. And then what happens is under the covers and behind the scenes, so secondary or out of band, what Cilium agent will do. And so if you're familiar with running Cilium, there's this little daemon set that runs on the node. It's written in Golang and takes care of administering the data plane on that particular node. What that will do is it will go create an MTLS connection to the Cilium agent that's on the node where the target service is, in this case pod B or service B. And it'll go create this MTLS connection, and it can use Spiffy. It can use those specs, the same spec that I talked about a second ago for identifying workloads in the and encoding that into the certificates. So we'll do an MTLS handshake here, and then if that succeeds, then we'll mark this little cache on the node that this flow is authenticated. But what's interesting and slightly unique about this approach is that the MTLS connection, I think I show here, and this is TLS 1.2, but in TLS 1.3, what ends up happening is the handshake occurs and then is terminated. All right, we do the handshake part and show that things have been authenticated, but then we stop. All the keys that have been negotiated, that's for the session. Those get dropped, and no data actually flows over that transport. So the connection here is only used to verify authentication, and then the answer is written into this little cache, and then from there, the expectation is the TCP retries will kick in, and eventually, as we come back, I think that's in the next diagram here. When the retry kicks in, and the packet tries to flow again, when the eBPF data plane checks, hey, is this authenticated by looking in this little cache? It says yes, then the flow will continue, right? And in this case, this is completely separate from what MTLS or the TLS spec says, right? So now this is its own data plane. It's its own, how the traffic proceeds is unrelated to TLS or MTLS in this case. And by default, out of the box, this traffic would proceed unencrypted. So you have the MTLS handshake that gets finished, mark in the cache, thumbs up is authenticated, and then the traffic can continue to flow. Right now, if you want encryption, then you can enable what most CNIs have already today, whether that's WireGuard or IPsec. You can enable encryption between the nodes. But as of today, it does not exist that the session keys between two workload peers are used to encrypt the traffic and can only be seen by those two peers. That can be seen by anybody on those nodes. I know that they are, ISO is working on what that looks like in the future, but that's what it looks like today. Now, that's all good and well, right? So that's how things get implemented. But under the covers, the actual identity model used in Cilium and on which this mutual authentication is layered, actually, it's the IP mapping to Cilium identity integer that we discussed at the beginning. And this is where things can get a little bit confused, right? Because as you know, in a dynamic environment like Kubernetes, pods are deployed, they're shut down, they are churning, and IPs are cycled and recycled. Now, that's all fine, but what ends up happening in Cilium is that this cache that's used to map IPs to the Cilium identity object, which is this is the core of Cilium's identity model. That map exists, that cache exists on every single node in the Kubernetes cluster. So every node tries to keep updated what the cache should be. So think of it as a global cache, but it has to be updated on every single node, and it should be consistent. And here's where the eventual consistency challenges come into the picture, because in a distributed system, unless you're using some sort of atomic operation or transaction or something, these will be eventually consistent. There will be times, for whatever reason, that the cache will be stale. That could be because of network slowness. That could be because the cluster is so big, the Cilium agent's taking a long time to process these updates and update the cache. This could be because there's temporary glitches in the network between the node and the Kube API, and others, right? There's a number of reasons why in a distributed system, you have to take time into account. And in this case, there can be scenarios where IPs could get recycled, assigned to a different Cilium identity, and traffic could proceed between two services when it's supposed to be disallowed. So if we take a look at a demo, now hopefully I set up this demo correctly. Where is, we should see this eventual consistency kick in, right? In my demo, I'm going to start off with a couple of simple services: Hello World v1, v2, and then Sleep v1 and v2. All right. Now, at the moment, if I call, so think the clients are Sleep, the servers are Hello Worlds, and they're different versions. If I call them in the various combinations that I can, all of the connections succeed. And that's fine because I don't have any network policies in place to restrict the connectivity or the activity between these services. But if we say that only Sleep v1 can only talk to Hello World v1, and Sleep v2 can only talk to Hello World v2, then we have to enforce those policies. Those could be for regulatory reasons. What we're going to do is we're going to set up a Cilium network policy to make sure that is the case, and we're going to use Cilium's mutual authentication. We'll enable mutual authentication as well. We can see here that that's the flag for enabling mutual authentication, and we're going to say that for the Hello World v1 service, only traffic coming in from Sleep v1 is allowed. And if we look at the Hello World v2, we'll do the same thing just for Hello World v2. But you'll notice again, authentication is required. Mutual authentication.
So, Christian, just a question from Kareem. He's asking if these pods have different identities. And
yeah,
the answer is
yes. Let's look.
Yeah.
Let's look. Watch. Here we go. So let's apply these resources. And now when we make a call, those calls, we'll see two things. One, that the policies are enforced, and two, if my demo automation is going to cooperate here, we'll see that the traffic between the Cilium agents, those Golang processes that live on as a daemon set on each node, will create a MTLS handshake to do the authentication part. So cross fingers. This doesn't always cooperate. We'll skip setting digging into Hubble here, but let's make some calls. All right, we haven't that's one of those pre-handshakes that are not part of the apps. So let's make some calls. We'll make 4 calls. That one, 1, 2, 3, 4, and we see that Hello World v1 on the top can call, or sorry, Sleep v1 can call Hello World v1, that we cannot call Hello World v2, and that Hello World v1 cannot be called by Sleep v2. Hello World v2 can be called by Sleep v2. That's what we were expecting. And we can see that there were also 4, authentication attempts between the agents.
So, question from Mike. He's asking, why are they using? Well, let me read it. So I'll read it verbatim. Why are they using not use OAuth for workload identity? So RFC 8705 defines OAuth 2.0 mutual TLS client authentication and certificate bound access tokens. Why are they using Cilium to define policies about which apps can talk to each other? Wouldn't it be better to use OAuth for workload identity? And then
So again, this is right now what we're doing is we're using Spiffy for workload identity by issuing certificates that have been assigned to these particular workloads, and using eBPF under the covers to enforce the network policy. So this is outside of OAuth, obviously, and layered on top of Spiffy. Hopefully that clarifies what Cilium's doing.
Yeah, Mike, feel free to add, like, say if it answered your questions or not. But yeah.
Right. Okay. So we can see that the networking policy between services that we expect is enforced. And now I think there was a question earlier about the Cilium identities. If we look at the Cilium identities, we see that there are 4 different Cilium identities. We had 4 different services. And if we look at the Cilium identity representing Sleep V1, we can see that it is this integer that I mentioned. This is 22533. This integer, the Cilium identity integer, represents the Sleep V1 set of services. If we look at it specifically, we can see that it's captured by these set of labels that are associated with the pod and metadata associated with the pod. Now, if we look inside one of those Cilium agents, we can see that for this particular Cilium identity, it gets mapped to this IP address. All right, so this is what we talked about a little bit earlier. Now, if I scale up the number of Sleep V1 replicas, we'll give it a second. Might take a second, but we'll scale up Sleep V1 so that we have 15 replicas of Sleep V1. And we run that same command, we should see the cache indeed includes all 15 of those pod IP addresses that are associated with the Cilium identity. So this is what's used under the covers in Cilium to map workload identities. Right, the spiffy part was just at the mutual authentication layer where we were trying to authenticate at the handshake, MTLS handshake. But then all of that stuff is retired basically, and we fall into Cilium's default workload identity primitives, which is this approach here. Now, as I mentioned, since this is based on IP mappings that are in a cache on every single node in the cluster, in a world where things are highly distributed and the expectation is that every cache is eventually consistent, can we get into a scenario where IPs are not cache, they're not the most recent updates in the cache? And to do this, let's look at this part where, remember, we had 15 Sleep V1s. We had 15 different IP addresses. Now, what we're going to do is we're going to simulate a temporary interruption between the Kubernetes node where Sleep, or I guess this is where Hello World V1 runs. And what that means is for the time period where this network interruption is there, we will see stale caching. And actually, my colleague Lynn's son, if we go into this article right here, walks through this very specific scenario. And so you would be able to walk through this as well. Maybe Peter, I can send this to you. We can link this into the docs. But there's a number of scenarios that we could hit where this connectivity could slow down or become intermittent or go down completely, and so on, that could get into this state. So now we're going to run a test now that shows what happens if there's churn, and we're going to recycle some of the pods and try to find a scenario where sleep v2 ends up with an IP address that was once belonged to sleep v1. And then we're going to try to call from sleep v2 to hello world v1. Now that call should not proceed, but we're going to find that in our tests and cycling through some of the pods, that sleep v2 got assigned an IP address that once belonged to sleep v1, and now can call hello world v1, which we don't want. We want to disallow this. And so this is what I mean, where the caches can get incoherent and things can slip through, and we don't want that. So this is where the service mesh can come into the picture, right? Where this churn and IP address mapping to the underlying fundamental unit of identity can get out of sync. We want to try to avoid that. Now, for example, in Istio today, if you deploy with the sidecars, then what you see is there is no mapping. There is no caching that we have to take into account or try to figure out on the wire. On the wire, when the connection is opened, we're already using the identity in the MTLS certificates, and that's propagated through to the other side, and the transport secure and so on. So we don't have this mapping. It's effectively stateless, right? There's no state that we have to take into account to verify whether things are authenticated. It's on the wire at runtime. Now in ambient mode in Istio, which is the sidecar-less data plane in Istio, which looks a little bit more like this. The traffic going from a workload needs to get mapped up to the corresponding MTLS certificates. And in the initial POC versions of ambient, where we used Envoy proxy as the Z tunnel and all that stuff, all that's been rewritten. We've made quite a bit of advancements and all that. Then we did have this sort of trivial implementation where we did basic mapping between IP addresses to find out what certificate to present. In revised versions of Istio, this is actually what it looks like. I'll actually draw it out for you right now. So come over here. Oh, let's find a blank spot. So in revised versions of Istio ambient, what ends up happening is the Z tunnel, which runs in its own network namespace, is actually mapped. It's port mapped into the network namespace of the pod here. So in this case, application A. And what ends up happening is when the application A wants to talk out to in this case, application C, the traffic will flow through these ports that are living in the network namespace of app A to the Z tunnel. The Z tunnel will choose the right certificate to represent application A. And then the data that comes out of application A will look like it's coming directly out of application A. So the Z tunnel does this certificate mapping inside the pods and workloads network namespace of application A. And then as traffic is leaving, this part actually gets updated. The traffic is leaving directly from the pod, right? So there's no IP address mapping or container UID mapping or anything like that. All of this happens in the network namespace of the pod, And as the traffic's leaving, we'll go directly to, actually, so the same thing would have to be the case over here. Directly to the pod. And so our MTLS connection will happen directly between the pods, just like it does in the sidecar approach. Now we use ZTON under the covers to facilitate that, but the traffic is going pod to pod. So we don't have this mapping of IP addresses problem. So what we end up seeing in ambient is if we kind of reset to a state where we're going to go back through this demo, what we're going to do is we're going to install Istio ambient, hopefully. Why don't we come over here and take a look at the Istio system namespace. Little by little, things should come up, crossing fingers. You know, you never know with live demos, but we see the ztunnel component here that I mentioned. Okay, so that come up. And now what we're going to do is we're going to configure Istio with those similar policies. So we'll leave the Cilium policies in place, but we'll configure Istio with those similar policies that Sleep v1 can talk to Hello World v1, Sleep v2 can talk to Hello World v2, but no cross version communication. So we'll do that using Istio's authorization policies. We will check that our connectivity, crossing fingers, okay, our connectivity is what we expect. V1s can talk to each other, V2s can talk to each other, but not cross version. And now we're going to demo that same scenario where we churn the cluster and get it into a state where a Sleep v1 IP address is now assigned to a Sleep v2 workload. And we're going to try the communication in that case, where we saw previously it would be allowed because of the IP cache incoherency. But now, since the workload and the workload identity and mutual authentication happens between the two pods directly on the wire, on the connection, without regard to any of that extra state, we should see the policies are enforced correctly. Let's cross our fingers. First of all, it might take a second to find as we churn the pods and try to get the IP address mismatch. That might take a second.
So just to confirm, this is a cluster that still has Cilium installed as well.
Still has Cilium. It was the same.
And there was so it's a combination of both, right, being installed on the same cluster.
So we still have Cilium network policies, the same ones that we had in place before. We do see a Sleep v1 pod IP address that was assigned to a Sleep v2 pod. We tried the connection. We tried to make the call, and this time it failed because those are not authorized to communicate with each other. So this illustrates fundamental defense in depth, right? Mm-hmm. Have your container firewalling, your network policies in place, but then also have and double check from a zero trust perspective that workloads are authenticated between each other and authorized between each other.
Yeah,
I think that's what I wanted to cover, right?
So do you know if this is like available already in the upstream ambient, or is this a different build?
That is a good question. Here, I'm having some headphones, silly Apple headphones. Here, give me a second. Let me switch to. All right, you should still be able to hear me.
Yep.
Okay. Right. So upstream in Istio ambient, we at Solo we've had this in place for what are we in December? So probably 7 months now, 6-7 months, something like that. in our builds internally, but we started the process of getting this upstream in the recent Istio Ambient. Let's see if we can pull this forward. In a recent Istio Ambient meeting, we shared this exact design with the community. I think there's a PR opened, or if not, it will be very shortly. That solves this pod and zTunnel traffic redirection for Cilium, but any CNI, right? So any CNI that we need to support should work with, and we've tested this with OpenShift, with Calico, with VPC CNI, with Cilium, with a number of popular Weave, and a number of popular CNIs.
Yeah, I think I found the PR. It's already there. I think that's the. I'll post it. I think that's the one. 48253. It's in. I guess it's still open. It's in the review, but
yeah,
it's getting there, right?
Yeah.
Perfect. Yeah, it's an interesting way of showing, right? As you said, defense in depth, right? The layers of the onion, right? It always makes sense to add like another layer on top of it, right? To make sure that the layer inside is not like to protect from what could go wrong in the layer inside, I guess, in a way.
Yeah. And I just want to point out that, here at what we work on, me representing Solo here, that, we work on Cilium, we work on Service Mesh. We understand how they both kind of fit and come together, especially in highly regulated enterprise environments. And there are these, differences in opinion and design between what we're doing and what other companies are doing. But what we've seen is in our customers, they need certain implementations. They have to be FIPS compliant. They have to be, secure, and defense in depth needs to be in place, and so on. So, I mean, if there's questions to follow up afterward, please reach out. We're happy to, if nothing else, just educate.
Yeah, exactly. I'm looking. There's no more questions. If there are any, feel free to post them. If not, I mean, you can reach out to Christian on Twitter. Reach out to me, Solo community as well. Slack.solo.io. You can reach both of us there and other Solo people as well. Mike has another question. So he's saying, in my opinion, we should use MTLS, but bind the OAuth access token to the MTLS client cert. The OAuth access token conveys the workloads identity in a much richer, more flexible way. By centralizing policy management, we can define policies about what workloads should be able to call each other rather than express policies in the service mesh.
Well, so Mike, reach out to me offline. There's a number of things that you're saying there where we can do things to bind certain ID tokens or access tokens into policies. We can reach into, I know we have a number of customers that are running Open Policy Agent to help with some of that. But I'd be happy to chat more about what that would look like.
Yeah. I mean, Mesh is extensible. Envoy is extensible, right? So you can plug in your own things if you want, right, to do the processing outside as well, right? But still use the service mesh, right, to call it out.
Yeah.
All right. Well, thanks, Christian. Thanks for taking the time. Thanks, everyone, for listening. Thanks for the questions, and hope everyone has great holidays. Great New Year, and we'll see you in January with a hoot number 64. It will be that time.
And I think there's a number of really good topics coming up in January.
Yes, there's a lot of stuff that we'll be doing. So hoping everyone will join us then as well. All right. Good. Thanks, everyone.
Thanks.